In this video, we're going to start a series that focuses on how we quantify compounds and perform reactions when our materials are dissolved in something. That something is almost always going to be water, and it should be fairly obvious why this is an important condition to learn about. All life on this planet is water-based, and the chemical reactions that sustain life tend to depend on compounds reacting in the presence of water, as opposed to as dry powders and solid chunks like we've been considering so far. Beyond that biological application, it's often much more convenient to do bench chemistry in solution too. You don't have to worry about melting or grinding solid compounds together in order to get a reaction to go. So to get started, we need to imagine what will happen to the different types of compounds that we've been studying when we try to put them into water. Just one initial point of order, we're going to call the thing that is going to be dissolved the solute, and the thing that is doing the dissolving, and that'll be water in all of our cases here, the solvent. And we're always going to assume that we have more of the solvent than the solute, by definition. For the sake of going in chronological order, let's begin with ionic compounds as our solute in question. Remember, an ionic compound is typically going to start out as a crystalline solid, with its ions held together by ionic forces. And we know from our earlier discussion of intermolecular forces that ionic forces are strong. Even so, it turns out that water tends to be a really good solvent for lots of ionic compounds. So here's how that works. On a surface level, there are three different types of possible interactions here. First, we have the ions interacting with each other in the solid. Then we have the water molecules on their own, and hopefully you'll remember that they can hydrogen bond. There's also a third possibility, the water molecules interacting with the ions, initially at the surface of the ionic solid. Those would be ion dipole forces. In our previous unit, we ranked these types of interactions by relative strength, and if we do that again here, we find that the ion dipole forces are the middle option. Compounds tend to like to settle down into interactions that are as strong and stable as possible. So from that point of view, the water molecules would gain stability by interacting with the ions, while the ions, at least on an individual level, are going to preferentially interact with each other rather than the water. Except there's an extra bonus for the water in this case. Because there's so much more water in this system than ions, multiple water molecules are available to surround each ion that becomes detached from the ionic lattice. And in this way, you're often likely to end up with a way more favorable state than you had before if you split up the ions and let them each interact with a cluster of water molecules. It's going to depend on how strong and how numerous those ionic bonds in the solute are, and not all ionic compounds are soluble in water. But if the energetics work out like we just described, your ionic compound is going to dissolve in water. The water molecules will pull the lattice apart like Lego bricks, giving you free ions in solution. For a soluble ionic compound like sodium chloride, we could write this dissolution reaction a couple of different ways. One way would be to simply change the phase of the sodium chloride in our chemical equation. The little AQ abbreviation tells us that this was an ionic solid compound that is now in aqueous solution, meaning that it's been dissolved in water. This is a valid way to express what's happening, but in order to draw a more explicitly accurate picture, we could also write the products as the separate ions that this compound separates into. After all, this is what's really happening, and if we try to do a reaction in this solution, it's the free ions that are available for reacting, not the solid ionic compound. We'll do more work with these chemical equations in a later video. Before moving on, though, it's important to recognize one more little detail. Say you were going to rewrite the products in this example as their separate ions to more fully show what's happening. Recognize that this ionic compound has 4 total ions in the formula, even though you only see 2 element symbols. If it splits up into free ions when you add water, you're going to get 1 iron ion and 3 chloride ions, right? So you'll need to be sure to change those subscripts in the ionic formula into coefficients when writing the free ions. Alright, so that's ionic compounds as solutes. What about molecular compounds? Well, the same principles apply here. Molecular solids are held together by intermolecular forces just like ionic solids. But for typical molecular solids, those forces are weaker, maybe hydrogen bonds or dipole-dipole forces holding the individual molecules together. Depending on the structure of the solid and the strength of the IMFs that hold it together, it's certainly possible that a solvent like water will also be able to pull that molecular lattice apart, just like it did with the ionic compounds. There's an important difference here, though. When an ionic compound dissolves, it breaks up into its free ions. And because of the way we write ionic formulas, that means that the compound's chemical formula actually breaks apart. Molecular solids usually don't do this. Sure, their IMFs are disrupted by water and the solid lattice breaks apart, but all that's happening is that individual molecules are separating from each other. The solid dissolves, but the chemical formulas don't change at all. So for ionic compounds, dissolution means splitting the formula into free ions, but for most molecular compounds, we would just write that the compound is going from a solid phase to an aqueous phase. There's a huge diversity of different kinds of molecules, though, and there are a couple of exceptions to this pattern. Acids were a subset of molecules that we studied in our previous unit, and they had a unique kind of interaction with water. If you drop an acid into solution, it will dissolve into individual acid molecules first, just like we saw in our generic example. After that, though, the structure of an acid makes it so that a water molecule can actually steal a hydrogen ion away from it, forming a positive hydronium ion and a negatively charged anion. Almost all the acids we've studied so far will break up like this completely, and we call them strong acids because of this behavior. There is a category of weak acids that we haven't seen before, and another category of a related type of compound called weak bases that both do this ion-forming behavior, but only to a certain extent, so that there's always a mixture of neutral and charged compounds in solution at any given time. You'll study weak acids and bases much more in Gen Chem 2. But for now, the only thing that you'll want to be able to do is recognize the formulas of some common examples. For now, if you see a chemical formula that includes a COOH, you're looking at a weak acid. And one example of a weak base that we'll see in this unit is ammonia, or NH3. Before we go, let's assign some categories to the behaviors we've seen. Something that completely breaks up into ions in solution is called a strong electrolyte in chemistry. Based on what we've seen, we'd put our soluble ionic compounds and our strong acids into this category. On the other hand, something that dissolves but doesn't produce any ions in solution is called a non-electrolyte. Most standard molecular compounds go into that category. Then, just as we briefly mentioned, there's also a category in between called weak electrolytes. These are compounds that partially break down into ions in solution, but not all the way. We'll put the weak acids and weak bases into this category. So in this video, we've taken a conceptual look at how different types of compounds behave when we dissolve them in water. Next time, we'll look at how you can decide whether a compound will dissolve at all in the first place, and start looking into some reactions that depend specifically on knowing about solubility. See you then.